How many chapters?
Course.
The course.
4th chapter.
Good. Which chapter are we finishing now?
Hartree-Fock about that.
Yes. Are we all happy about Hartree-Fock? Did we have enough? Will we be able to fill the flowchart? Or you found something is missing there? I suggest we look on it briefly, just without too much concentration, double check that we do not miss anything important on this flowchart, that we have all components. Just by thinking back in the airplane, I noticed that one little piece is missed. And if you look on it, it will be good for all of us. So we will spend maybe 5 minutes on overviewing this flowchart once again, and fixing the holes. And then the main goal announced in this course was to generate observables, to characterize materials. And you may develop a feeling of irritation, like the instructor promised observables and we are going series to series to series. Where are observables? So we need to spend a little bit of time on observables, at least in not only in the lab but in the practice, in the lecture time. So we will cover a couple of observables that can be generated based on Hartree-Fock theory. If technology allows, I will try to do the same organization as usual, scratching something on board, then switching to content. And if technology doesn't allow, it will be either one of those. Content, come up. Content, come up. Content. Whew. So, as any electronic structure theory, one may want to compute total energy, which will include energies of molecular orbitals plus the electron-electron interaction energy. So this first equation shows it, and there are no problems with it. All indices count electrons and go only for electron-electron interaction, go only up to highest occupied orbital. All good, no problems here, no flows in the board. But when we develop this flowchart, there is a little missed item, or it's not a big paradox, but it is a thing that we haven't focused. When we formulate Fock matrix, it is formulated in the basis of atomic orbitals. But it needs to take into account influence of many electrons. And electrons are distributed over molecular orbitals. So Fock matrix that we are using in the self-consistent cycle should include information about molecular orbitals and occupation of molecular orbitals. But formally, it's just 3 letters: F, mu, nu. F, Fock, mu, nu, atomic orbitals. Where are molecular orbitals and where are the occupations of molecular orbitals? So when we set up an equation for Fock operator, there were no paradoxes because we didn't set up any basis. Do you have
No.
materials from last time?
No.
Do you know what you are presenting in a week from now?
No.
Does anyone know? One. Oh, this is nothing, but but this is really important. So let me just satisfy. Yeah, let's take a seat. Satisfy my own curiosity. Whitney present Perl scripts to extract density of states out of .log files. I think it was one of your choices.
I think so. I don't know.
Okay, so when we formulate fork operator, there are no paradoxes because there are no bases. But if you go to specific bases, atomic orbitals or Gaussian orbitals that look like atomic orbitals, we need to take into account knowledge about molecular orbitals that are already at our disposition. But the object that we construct should depend formally only on atomic orbitals. How do we do it? We do attribute a weighting coefficient in front of matrix elements of the electron-electron interaction in such form that it will include products of the molecular orbitals with a trick. There will be summation over all molecular orbital indices, and the atomic orbital indices will stay untouched. Then it will be an object that depends only on atomic indices, but it will contain information about molecular orbitals. So it is a way how to bring in information about how electrons sit on different molecular orbitals and create background field. So if we add this object, which some people call a density matrix, it is not general density matrix, it is Hartree-Fock specific density matrix. Then one formulates Fock matrix that does depend on atomic orbital indices. And this first term is kinetic energy of a single electron and attraction to all ions. So this is an equation from the page from a book. So if we add this specific form of Fock operator, then we can try to feel what? To feel a flowchart. Content go away. Content go away. Stop content. So let me do your homework. So the number of boxes is not coinciding with what is on your stuff, so you may need to redraw it or alter it. So we start from positions. Then, in addition to positions, one needs to have a random guess for molecular orbitals. This information serves as an input to self-consistent cycle. At the end of self-consistent cycle, we can find observables. first we need to formulate choose basis. One needs to formulate density metrics. Density metrics. Which will depend only on atomic indices. Then, upon we formulated, or stored, programmed, upon we have a piece of data, array of data representing density metrics, we are formulating Folk operator. So, which observables are we going to? Well, electrochemistry, ionization experiments measure the ionization energy and electron affinity. This has some relation to real life. So we will cover these two. And another observable that characterizes materials is spectra. So the molecules, the materials that we do describe with electronic structure theory may have ability to interact with light. And then we need to introduce a rigorous form for the molecule with known total energy, known expansion coefficients, known energies of individual orbitals, ability of such molecule that has been characterized from electronic structure point of view to interact with light. What is light?
Electromagnetic radiation.
What is electron and what is magnetic?
They're perpendicular.
Yes, but what are they? The one word is missing.
Waves.
Then another word is missing. Like
Oscillate.
what does oscillate if we have a propagating electromagnetic wave? Huh? Not part. There is a specific word that is required. Huh?
Amplitude.
Amplitude of what?
Electron.
Energy. Photon.
More. I can even waves. It's interesting. So waves. What? Electron. Photon. Amplitude. All sounds very scientific. So when electromagnetic wave is propagating, something is perpendicular something is oscillating, and even the best saying was electro and magnetic parts. Parts.
Fields.
Yes. Black frame, not because we want to worry it. So, what is the field? It's a force. So, electric field is that in a specific area of space, there is some force that would affect on any charged particle, pushing it in a specific direction. Therefore, it is drawn by vectors. So if an electron is placed there, it will be pushed up. And if it is electric or electromagnetic wave, it means that this force, this electric field, will change as we go to different regions of space. So it will be smaller, 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 then it will start getting negative, then again positive, positive, negative. So this E for electric field. Part, amplitude, oscillating, photon, electron, waves.
It's not an electron.
No? Okay, I agree. Perpendicular. At the same time, there is another vector that would affect an arrow of a compass. Okay. And what is drawn right now is expressed at a specific time. But as time passes by, the lobes and nodes are moving forward with the speed of light. Where is our molecule? It is on the way of this photon. So here is our molecule. Atoms, bonds. No, I will tell you the joke right now. Otherwise, I will forget it. I was on a conference of software developers. I don't know how I got there. Here is their like program. And at the end of the meeting, they had a little social. And one of the old guys told a joke. When he was younger, he interacted with, as a quantum chemist, he did interact with a Nobel Prize holder in physics. And it was like 30, 40 years ago when computational chemistry was really underdeveloped. And there were equations, there were slow solving, but rendering of atomic models, building of atomic models was a big problem. Because making this three-dimensional visualization takes a lot of compute power. And then this person told his personal story, like, I hired a postdoc who could make a rendering showing for atomic positions with this coordinate, showing some objects that you can rotate, click, and add. And this postdoc was just starting this project and already did a great success. But in order to save computational resources, he represented each atom with cubes. Because cubes take much less numerical effort to show that different facets are irradiated by light differently, and one can make a three-dimensional effect. And then the person who tells the story decided to impress his senior friend, physicist, this press and tell, look at here, what we do, how nice it is. And it was like benzene molecule or carbons and hydrogens are represented by little cubes, rotating, showing, and this physics person asks, is it exact? Is it quantum solution of quantum theory? And the person, the speaker, answered, oh yeah, sure. There are Hartree-Fock, there are self-consistency, there's quantum, there are orbitals. And the physics person was doing completely different things. It is quantum. And I always thought that atoms are spherical. Is it singularities in specific direction? How come that from quantum solution you get a cubic atoms? So here are cubic atoms on the way of our electromagnetic wave. What does it mean the light interacts with matter? Or what does it mean something X interacted with Y?
Dipole.
You are running in front of the car.
Is that bad?
No, it is good. Well, it is an answer of the whole story that I'm going to make for. But more generally, in specific to optics, what or light to matter interaction, what does it mean that two species are interacting?
Energy transfer.
Energy was good. Energy plus transfer. Minus of question mark. Like, forget about physics and light. If you just have two molecules, binding, energy, right? So if something is interacting, one can always assign specific energy of interaction. So one needs to specify energy of interaction between light, between this arrows of electric field and molecule. It doesn't matter which letter you use. One can use H, F, V. Now we are listening to Levi, who told this word. So molecules can be completely neutral, can be dipolar, and generally, if we do have electric field, and if we do have a dipole, there is a specific energy of their interaction, right? So this electric field dot product to the dipole. This is not a discovery, it was always so. But the only difference is that now we have a rapidly changing electric field, and we are having specific brand of a dipole. It's not a dipole that resides always on a molecule. It is a dipole that is forming when molecule is transferred from ground state to excited state. And it is so-called transition dipole. Transition dipole. Transition dipole. And since from our previous experience we know that by interaction between light and molecule comes from ground to excited state. Therefore, matrix element of coming from ground to excited must be non-zero if it doesn't interact with light.
Technically, wouldn't you just have to have one state going to another state, because you can have excited state absorption?
One can have excited state absorption, but if one doesn't disturb molecule for long enough, it will come to the ground. And it's reasonable to start from the ground. So we need to find a matrix element. And since electric field here is just a classical number, it is a function, it is a number, it is not an operator. We can put it up front and do cross dot product with matrix element of dipole. How does it relate to what we did before? There is an important logical aspect that we can skip and be happy until we meet a reviewer of a paper. Intuitively, we understand that by absorbing a photon, an electron from one orbital jumps to another one. This from one molecular orbital to another one. But is it rigorous enough? Does it matches all our previous saying about multi-electronic wave functions? Basically it is right, but we need a little justification to check whether we can use language of single electron orbitals to describe interaction of light with multi-electron molecules. So then what is our ground state? If you will do everything super rigorously with Slater determinants and Fock, we will spend longer time than we imagine. So let's go with Hartree products, with understanding that they are not super precise, but they give main concept. So ground state for, let's say, H2 molecule, or any object with two electrons, because otherwise it would be too complicated. So first, second, third. And let's count that spin index also is included here. So it is not two electrons on orbitals, it is just here and there, ground state. Then the excited can be one is translated from orbital one electron, to orbital 3. So by photon we went up. And if you want to have a little flavor of multi-electronic wave functions, we would write this one as a product of phi 1 times phi 2. And this one will be product of phi 1, phi 3. Multi-electronic wave functions. What about orbital? What about dipole operator? Dipole is electric charge times position, right? But here our position means summation of all electronic positions, and if one wants to be rigorous, minus summation of all ionic positions. So this will be dipole operator. And now we are going to merge to find the matrix element of this dipole operator between these two orbitals. So U between ground and excited. Three. One. Two. One. So by now, our approximations is that we do harder products, and that for simplicity we take two electrons only, but we can simply add summation over other electrons. So we are still with multi-electron approach. Integral over position of electron 1, integral over position of electron 2. Electron number 1, we start in orbital 1. Orbital electron number 2 in orbital, we start in electron 2 in orbital 3. R1 plus R2 multiplied by electron 1 in orbital 1, electron 2 in orbital 2. So these will be summation of two terms, one originating from R1, second from R2. So what do we see here? Let's focus on those parts of the first integral that do depend on R2. This little box, and integration over R2. So we do have molecular orbital number 3 of argument R2, molecular orbital number 2 of this argument, and integrated. G over 2, phi 3, phi 2. What is it equal to? What is it equal to?
Are we assuming what
Yes, they are good molecular orbitals that came out of diagonalization. See? Zero, yes. Those are not atomic, those are molecular orbitals. Be zero. And then we do not care about the rest. If you have a factor 0, then whatever is the rest doesn't count. So we identify this 3 red boxes that generate 0. Now let's look on the second term. If we look on everything that relates to electron at position 1, D R1, phi 1 R1, phi 1 R1. So orbital electron at position 1 occupying orbital number 1. So if the orbitals are orthogonal and normalized, then this will be equal to, yes, to 1.
We're doing the lazy wave.
Yeah. Then all this enchilada will be equal to what is not included into red boxes. E integral d r2 phi star 3 r2 r2 phi 2 r2. Which will be transition dipole matrix element between one electron molecular orbital. So it was a little maybe boring and spending your valuable time, but conclusion is that even if one starts with precise multi-electron wave functions, and one is looking for precisely defined dipole operator, taking into account multi-electronic nature. If we are exploring transitions associated with swap between two orbitals, the final contribution can be expressed in terms of one electron integrals of one electron molecular orbitals. So the picture of orbital electron going from orbital number 2 to orbital number 3 is, it was intuitively correct, and we have a justification to use this picture further. So although we know about multi-electron nature, we can neglect all electrons that are not involved in this transition, and they will not contribute to the matrix element characterizing the intensity of interaction of light to matter. So if you want to characterize light to matter interaction, it is sufficient to work in the basis of orbitals.
So it is true if electron excited by one.
What do you mean by?
I mean, suppose like one
We are not
electron
considering
excited
multiple
one
excitations. Huh?
Is it possible to excite two electrons, suppose like, or multiple electron at the same time?
It will be more complicated than this. Then you cannot work in the basis of single electron orbitals. The expression will be different. It will be products of such things. Okay, and even if we are not doing it immediately right now, we will come back to this very important subject again and again. So if we do have matrix element of interaction between light and matter, and we plug it into expression which is very similar to Fermi-Golden rule, it will generate the oscillator strength expression, which is something that is intuitively known from spectroscopic exercises in wet lab.
So what's V?
It is what we were looking for.
And then that's just the density of the electron? Or what?
Density of states. So if we continue from here on and work this expression in details, we will be able to compute absorption spectra of the material under the condition that electronic structure has been computed. So we do have electronic structure, we have molecular orbitals, there is a way to compute absorption spectrum. And it is not the last time we are talking about it. We will come to it with more details and come to practical skills of doing spectrum. Content appear. Content appear. So waves, then generally not cosine, but this exponentially with imaginary phase. So interaction of light to matter can be approximated by dipole term, is a leading term. There are additional terms, but they just add a little bit to precision. Dipole term is sufficient. Here is the formal definition of dipole. That means all positive positions of all positive charges minus positions of all negative charges. And then if we need a matrix element, formally we need to find matrix elements between Slater determinants, ground and excited. And if HP is not Hewlett-Packard, it is Hartree product here. So we simplifying our multi-electron operator by summation of this position operators, and we simplify our multi-electron wave function by Hartree product. And then we are looking for matrix element between ground and excited. So if we are carefully doing it, two terms in the operator gives us two terms for the matrix element, and in one matrix element we identify that orthogonality of orbitals evaluated at a space point different from which where we find the orbital, where we find the operator. So we are looking for R1 and we are integrating over R2, and then through orthogonality we get 0. And for second term, the orthogonality gives us 1. Therefore, first term drops completely, second term survives. And the only surviving part is one electron transition dipole matrix element. Or if we were in the quantum course from the beginning, expectation value matrix element of position operator, which is a key to characterize interaction of light to matter. Conclusion. Multi-electron observables can be represented in terms of one electron matrix elements. How are we doing with time? How are we doing with steam to speak a little more? I want to cover two things more today. So one will be very slow introduction into periodic materials, periodic solids that we will need to deal with. Even if we all chemists, we may need to deal with polymers, which are periodic. And if we deal with nanomaterials like surfaces, they are periodic. Nanowires, solids, it is a useful skill. So how do we define a periodic solid? So it will be boring to look on a screen. It will take a little longer time, but I better scratch on the board. Content disappear. Content. Okay. Now we are recording the cleaning effort. So intuitively, periodic means that if you have a couple of atoms, then if you go to the same size of the box and shift it by the same amount of translation, we can get absolutely the same repeating pattern. But can we make a shorthand notation? What does it mean for input for electronic structure? The ions contribute term of colonic attraction. Right? It does depend on position of electron. Which means that if here is our origin, the distance from the ion determines the potential, the attraction that electron is feeling from this ion. But if we suddenly consider position of electron that is shifted by the vector which is equal to the size of the box, so this will be R, then at this point electron will feel exactly the same potential. And more generally, one can place here any integer number. Integer number, and here is the box size, translation vector, periodicity. So potential at different point of space will be the same as one can find several points of space where the potential is exactly the same. And in this shorthand notation, we don't care how many ions is in the cell. We just state that it is a definition of periodic system. Content, appear. Good. So repeating periodic cell. There was universal scientist who contributed to the description of solids and nuclear magnetic resonance at the same time. And when he was dealing with solids, he derived that wave function found in the periodic potential will have a specific way, a specific shape. That when the potential is exactly repeating at a new space point, the wave function will be the same with precision up to a phase factor. So it will be absolute value of the wave function will be the same, but phase can be accumulated. And here is this expression. So the wave function in these periodic systems will be a product of the contribution from the vicinity of ion times envelope function that depends on going from one periodic cell to another one. And this atomic part will be the same, and periodic part will accumulate different phase. We are not going too much deeper into this. I just want to give heads up and scare you a little bit, but we will focus on it in more details, and we'll find that those are easy things. Just please start thinking in this direction on your background thinking. Okay, last part that I want to touch today, and we do have maybe 5-10 minutes. If you have photoelectron ejection of electrons from material, it will depend on the ionization energy, or if you just do electrochemistry, you can tune the voltage and find the oxidation reduction potentials that also correlate with affinity and ionization energy. And do we have any connection between these practical observables and the stuff we were exhausting ourselves and our computers? Yes, there is. So, how do we find the total energy of a molecule if we have completed Hartree-Fock calculations? We do content disappear. We set up total energy as summation of all occupied energies of all occupied orbitals, and then we add interaction energies between all pairs of electrons, or I and J indices are indices of molecular orbitals. There was a scientist with last name, and he told, we are so tired of these interactions. Let's approximate the negligible and make oversimplified, quick analysis and interpretation of the electronic structure calculations based on energies of molecular orbitals only. So it is not, we are missing substantial part of energy, but this approximation would allow immediate, quick estimate of the ionization and affinity. So, what will be the energy, total energy of a neutral molecule? It will be E1, E2, E3, E comma minus 1, E comma. So all orbitals until highest occupied molecular orbital. What will be the total energy of the anion? So anion means that we have removed one electron from the model. Means we picked it up from the highest occupied molecular orbital. One, two, three.
Cat on it, right?
Okay,
Yes.
Because if you kill a cat, it's good.
I just,
Cation.
I just go the T looks like a plus sign.
So we do have for neutral, we do have electrons on all orbitals, and we add together all their energies. Now, if you do have cation, we do remove one electron. So we have nothing on HOMO, and we have electron HOMO minus one, first, second, third, and anything in between. E1, E2, E3, E HOMO minus one. But we still need an ion.
Go to Lumo.
Yes. Minus one. E1, E2, E3. So HOMO minus one is occupied and we contribute its energy. HOMO is also occupied and we contribute its energy. And if it is anion, it means we contribute one more electron. It cannot, because of exclusion principle, it cannot sit on HOMO, so it goes to the LUMO orbit, to the next orbit. This one, HOMO, LUMO. Now, how do we define ionization energy? What is ionization? It means energy required to remove an electron.
So
Remove an electron, meaning that at the end we will have cation, at the beginning we will have neutral. Ionization energy. The energy of cation plus one minus energy of neutral, 0. This one minus this one. So all these terms you cancel and you get minus E. So if we have unlimited numerical facilities, we can directly compute energies of cations and anions, subtract them and get ionization energy. But what if we need to quickly estimate and we have only one run? We do not have time to recompute them again and again. We just take energies of molecular orbitals and the energy of highest occupied molecular orbital can correlate with ionization energy of the molecule measured on experiment. If it does, then it is very good. If it doesn't, we blame Putin.
But if we optimize the cation, it would give us a different ionization energy known as a adiabatic ionization.
Optimization will contribute its contribution. But the correction from taking into account multi-electron effects is more important. So even in best cases, the neglection of these terms gives is responsible for about 15% error. So it is quick estimate. If you don't care about 15%, one can do it. But if one needs to evaluate if a material is a good donor or good acceptor, it could be available. And same, electron affinity. How do we define it? Energy to stick an electron to the molecule, contribute additional electrons. So at the end, we'll have anion, at the beginning we have neutral. So energy of anion minus energy of neutral. So this one minus this one. So we cancel everything. And the only surviving term is the energy of lowest unoccupied molecular orbit. So properties of multi-electron molecules are expressed in terms of one electron orbitals. This is known as Hofmann. So if one can neglect electron-electron interactions, then it becomes correct. Are you happy?
Yeah.
It was a political, maybe you're not happy.
So it's known as a vertical ionization energy, maybe, right?
Yes, we do not take into account reorganization yet. It is only a single point calculation. Content appear. So if you neglect electron interaction, we total energy summation of occupied orbitals, and then we have neutral, anion, and cation, and by subtracting pairwise energies, we can estimate the energy of electron affinity and ionization energy. This was Koopman theorem. This was a lecture with a brief overview of observables. We are completing Hartree-Fock theory. So what are our plans? How do we proceed further? Oh, on Tuesday, please bring this little